The system of two rods in this figure is in equilibrium, so when perturbed, it will oscillate around this pivot, moving back and forth as a physical pendulum. That means the frequency of small oscillations will be 1 over 2 pi times the square root of mgd over the moment of inertia I. The system's mass, capital M, is the combined mass of the two rods. Each has mass little m, so the system's mass is twice that. D is the distance between the pivot and the center of mass. We see from symmetry that the center of mass lies along this vertical line, and it also lies along the line joining the centers of the two rods. So that intersection is shown here. This is the distance d, with these angles being 45 degrees. So that this leg also has a distance d. From the Pythagorean theorem, we then see that the distance d is the rod's length over 2 times square root of 2. The system's moment of inertia, capital I, is the moment of inertia of each rod as it pivots around this point. So we have twice the moment of inertia of a rod pivoted about its end. That's twice 1/3 ml squared, or 2/3 rod's mass times its length squared. Now we can substitute these three results into the expression above. We get 1 over 2 pi square root system's mass times g times L over 2 root 2 times the moment of inertia 2/3 ml squared. And now we simplify by canceling a 2 from numerator and denominator, canceling an m, and canceling an L. And rewriting to see the frequency is 1 over 2 pi square root of 3 over 2 root 2 g over L. If you multiply the numerator and denominator inside the radical by 2, you can rewrite this finally as 1 over 4 pi square root of 6 over root 2 g over L. That's about 3% higher than the corresponding simple pendulum result.